Hello, this is going to be our review session for exam 2 for Chem 112. Now this is going to cover chapter 16 and 17 of Brown and LeMay book. So I'll go over the type of questions you'd expect in exam. The first question that we'd like to discuss would be conjugate acid and base. This is a pretty simple question, would have an easy answer. Say I give you H3PO4. If I ask you what is the conjugate base for this, you just knock off one hydrogen out of here. When I knock off hydrogen as H plus, you end up with H2PO4 minus. Each time you knock off one hydrogen, you get -1, then -2. This is how it goes. So this is going to be the acid, conjugate acid. Let's write a CA for conjugate acid. And what you got after getting rid of hydrogen is called conjugate base. So this is conjugate acid-base pair. How do I go back from base to acid? By adding H plus. So if I add H plus, I get this. If my question is about H2PO4 minus, if I give you this and ask you that write down conjugate base for H2PO4 minus. Again, you're going to do the same thing. Get rid of H plus out of here. So that means instead of having H2, I would have HPO4. I got rid of one hydrogen as H plus, so this already has minus, so this becomes -2. So this is going to be now conjugate base, and this is the acid. I can write down conjugate acid. So this is conjugate acid-base pair. So simply by removing hydrogen from an acid, you get a base, or by adding hydrogen, you get an acid. So from this to this is minus H plus. From this one to this one is plus H plus. So keep that in mind. That's how we get conjugate acid-base pair. The next question I would like to discuss, so this is question number 1. About different definitions of acids and bases. So I would like you to know the definitions of acids and bases. Now in my lecture note, as well as in the book, you'd find that there are 3 different definitions we talked about. One is Arrhenius' definition. According to Arrhenius' definition, an acid is the substance that's going to give H plus in water solution. And base is the substance that would give OH minus in water solution. So that only deals with H plus and OH minus in water solution. But there are many other solutions other than water solutions. So you can't apply Arrhenius' definition in every case. So we'll have to have other definitions. So it's called Bronsted-Lowry definition. According to Bronsted-Lowry definition, an acid is a substance that gives up H plus. It could be any solution. And base is a substance that accepts H plus. So H plus is given off. Base accepts H plus. So acid gives off H plus, base accepts H plus. That's Bronsted-Lowry definition. It doesn't have to be a water solution. And in Lewis's definition, an acid is an acceptor of electron pair. So an acid accepts electron pair from another element, from another substance, and base donates electron pair. So these are the 3 definitions that we need to know. Now when we are talking about a strong acid or weak acid, make sure we understand it. Acid, weak acid. A strong acid is a substance, and if you go by Arrhenius' definition, that would readily give up H+. That's a strong acid. 100% of that substance would break down. Like for example, HCl is a strong acid. It would break down 100%. If I have 5 molecules of HCl in water, all 5 of them would break down. And that's why it's a strong acid. On the other hand, weak acid would not break down 100%. Only part of them, out of say 5, maybe one of them would break down. So that makes it weak acid. So that's true for even Bronsted-Lowry definition. In case of Bronsted-Lowry definition, a strong acid would readily give up H+. A base would readily accept H+. That's a strong base. So similarly, for Lewis's definition, is an electron pair. Now, we should also go over what would happen to the conjugate base of an acid. This is a strong acid. If I get Cl- out of it by getting rid of H+, that's a conjugate base. This is conjugate acid. Question is, what kind of base is this? Is it a strong base or weak base? Students often get confused. If this were a strong base, it would readily accept H+. Now question is, does it readily accept H+? Answer is no. Because if it readily accepts H+, then HCl would be would be a weak acid. That means it cannot break down. So in other words, for a strong acid, the base would be a weak conjugate base. So for a strong acid, base would be a weak conjugate. On the other hand, for weak acid, this is going to be strong. So make sure you understand this, because Cl- cannot hold on to H+. Because if it can hold on to H+, then this would be a weak acid. It would not break down. It's like your old furniture. You want to get rid of it, and once you get rid of it, you don't like to get it back. So HCl would like to get rid of hydrogen, which is like old furniture, and Cl- would not like to get it back. So that's why it's a weak base. A strong acid goes with weak conjugate base. Weak acid goes with a strong conjugate base. So keep that in mind. So there will be a word problem on this. So I'm now going for the next problem. Before I move to the next problem, I'd rather like you to know which ones are strong acids in Arrhenius' definition. In my lecture note also you get a series of compounds: HCl, HBr, HI, HNO3, H2SO4, the first acid, first hydrogen of H2SO4 is a strong acid. HClO4, these are all strong acids. They'll break down 100%. So make sure you check the list, and you need to know this. Now, I'll show you one typical reaction. Say HBr in water would break down into H plus Br minus. And that would happen 100%. In other words, if I have 1.0 moles per liter, which is molarity, of HBr at the beginning, if I give it some time to reach equilibrium, this would be close to zero. Nothing left. Everything would break down. And then I would get 1.0 of H plus and 1.0 molar Br minus. So that everything would break down. If one of HBr breaks down, I get one of H plus and one of Br minus. When 1.0 breaks down, I get 1.0 of H plus, 1.0 molar Br minus. So that's true for any of these acids, because they're strong acids, they'll break down 100%. So if I have 5 of them, all 5 of them will break down. So that's about the strong acids. What about the strong bases? group 1A and 2A hydroxides are strong bases. Group 1A and 2A hydroxides. Like for example, group 1A, sodium is a member of group 1A. Hydroxides, OH. How do I know it's NaOH? Sodium is +1, OH is -1. Now the question is, how do I know OH is -1? Think about H2O. In order to get OH, you get rid of one hydrogen as H+. So OH has to have -1. So this is +1. I can write down like this. This is -1. So my formula is NaOH. So I don't need to memorize the formula of each and every hydroxides. If I pick one from group 2, it would be calcium. Group 2A would have +2 on calcium. Again, OH would be -1. So the formula is going to be, this number would come down here, and 1 would come down here. So you have CaOH2. That's called calcium hydroxide. These are all strong bases. So what happens when I have a strong base in water? It would break down 100%, just like a strong acid. Calcium would get separated as 2+, aqueous. These are all in water solution, alcohol aqueous solution, plus 2OH minus aqueous solution. And that's going to happen 100%. There'll be nothing left here. So if I start with, say, 1.2 molar calcium hydroxide to begin with, at equilibrium, if I wait long enough, so initially there was no calcium, no OH minus. At equilibrium, this is going to be 0, because all of them would break down. So it's going to be 1.2 here, which is the same number as this, and OH minus will be 2 times of 1.2, because when one of these breaks down, you get one of these and 2 of these. So that needs to be maintained. When 1.2 breaks down, you get 2 times 1.2, which is 2.4 molar OH minus. So these are the reactions that you'd expect from strong acids or strong bases. For this exam, you need to know which ones are strong acids, which ones are strong bases. As I said, strong bases are pretty straightforward. Group 1A and 2A hydroxides. And acids, you need to basically remember them. Organic acids are mostly weak acids. That means they would not break down 100%. So we are going to do some problems, then you have better understanding of how to do problems with strong acids, strong bases, weak acids, and weak bases. So the next problem that I'm going to do would be pH calculation. Okay, that's going to be pH calculation of acids and bases. pH calculation. First, I'm going to talk about pH calculation of a strong acid. Now, that strong acid could be HNO3, could be any of these. Okay, so let's assume that I'm picking HNO3. So the question is, I have 0.20 molar HNO3. And what is the pH value? In exam, you have to recognize that this is a strong acid, because it's like coming from all those lists of strong acids. So keeping that in mind, that this is a strong acid, and it would break down 100%. So you can write down like this. HNO3, that would break down H plus NO3 minus. And that's going to happen 100%. So I would have initial, when it didn't have a chance, you just add it in water, 0.20 molar. And at that point, there was no H plus or NO3 minus. At equilibrium means you give it enough time, which will be pretty quick in this case, because it's all breakdown. All of these would break down. 0.20 would break down from here, so nothing would be left here. Because it's a strong acid. So let's write down here so that we all know that. It's strong acid, and that's why nothing will be left at equilibrium. When 1 mole of HNO3 reacts, you get, let's write down these, this is the balanced reaction. You get 1 of H plus and 1 of NO3 minus. When 0.20 molar breaks down, it will be the same number. So I get 0.20 molar of H plus and 0.20 molar of NO3 minus. That will be the important step for this calculation. For pH calculation, this is the value that we are interested in. So we can write down our pH would be given by minus log of H plus concentration. This is log with respect to base 10. So this would be minus log of 0.20. So then you need to know how to use your calculator. Normally when you write down log, that means base 10. So make sure you practice doing this kind of problem. And this is the number that I got. So make sure you double check my number. 0.699, and I'm going to round it off to 0.70. So that's the pH when you have 0.20. So keep this in mind. This is the pH of a strong acid. So let's write down here. pH of a strong acid. What happened in this case? There was a 100% breakdown. And we got all the hydrogen coming from that strong acid. And this goes in your calculation. So as if it's actually the same number because it's 1-on-1 reaction. If in my formula I had H2, of course there is no compound with H2NO3, but if in my formula I had H2, then there would be 2H plus. And this would be 2 times greater than this number. Then that 0.40 would go in your calculation rather than 0.20. Okay, so this is pH of a strong acid. Now we're going to discuss about pH of a weak acid. So the pH, instead of, we're going to use the same molarity. Weak acid. So we're going to use a weak acid, and we're going to pH. Okay, so we're going to use a pH of a weak acid. Now we're going to consider acetic acid to be our weak acid. Now, many of you may not be familiar with all these organic acids. So, say for example, this formula is given to you, HC2H3O2, and the name is acetic acid. We can write down this formula in many ways. Like another way would be CH3COOH. In an organic chemistry book, that's how you'd see this name. But one of the hydrogens is acidic, that means it breaks down. The other hydrogens don't. So I can write down like this. Once you see the formula, you should know right away that this is not going to be a strong acid, because the strong acid would be on that list of like 7, 8 acids, HCl, HBr, HNO3. Since it is not one of them, right away you can say, without even memorizing all these information, you can say, okay, this must be a weak acid. And so you treat it as a weak acid. Either you can use this whole formula, or you can write it down as HA. It's a symbolic thing. A represents C2H3O2. So we often do that so that it's easy for us to write. So we can write down HA breaking down into H plus A minus. And if you want to use the exact formula, then you can, it's all also possible to write down like this. There's nothing wrong. H plus C2H3O2 minus. Both are right. This is a symbolic way of writing down the same compound. It's the acidic acid. So here we know that initial concentration is say 0.20. This is 0.20 molar. At that time, it didn't have a chance to break down when you just added. So you have a 0H plus and 0 A minus. And equilibrium. Remember, for a strong acid, we had 0 here because all these broke down. But this is not a strong acid. All of them would not break down. Only part of these would break down. A few molecules would break down. Question is, do I know at this point how much would break down? Answer is no. So you'll have to assume that X is the amount that breaks down. So assume that X breaks down or dissociates. What that means is, rather than saying that you have all 0.20 molar breaking down because it's not a strong acid, I would rather say out of these 0.20, X is the amount of HA that is going to break down to give H plus and O minus. Now, if X breaks down, how much is left over? 0.20 minus X. And that leftover concentration is called equilibrium concentration. So X breaks down, so this is going to be the remaining concentration. Think it this way. If you have $10 in the pocket, and if you spend $2, how much is left over? 10 minus 2. So here, initially, this compound had the concentration of 0.20. Out of that, X amount was spent or used up so that it makes the product. So this is going to be the leftover, and that leftover concentration would be equilibrium concentration. Next, we need to know if X amount of HA breaks down, how much H plus are you going to get? It goes like this: 1, 1, and 1. If 1 of HA breaks down, you get 1 of H plus and 1 of A minus. When X is the amount that breaks down, you get X here and X here. So make sure you understand that. And now I can set up an equilibrium expression. In this case, it's going to be, this is an acidic reaction. K equilibrium, we're going to write down as Ka. A for acidic reaction. In this chapter, you see a lot of these different subscripts. A for acid, B for base, so Ka means equilibrium involving H plus, which is an acidic reaction. So this time this, so let's write down the original expression, H plus times A minus divided by HA. These are all raised to the power 1 because these coefficients are all 1. And I can now write down X times X. H plus is X times X divided by 0.20 minus X. So what you're going to have is X squared divided by 0.20 minus X. So that's the expression, and in a problem like this, Ka value has to be given. Otherwise, you cannot do this calculation. So for the time being, let's assume that Ka is given, and Ka is, I'm going to write down, Ka value is 1.0 times 10 to the negative 5. And that has to be given. Otherwise, you cannot do the problem. So in exam, I'll give you the value, either together with the question or at the very front of the exam. You would have these given values. Or you can have a data sheet. For online class, you'd have a data sheet where you'd have all these Ka values of different acids. And back of the book also has the listing of these values. So now let's write down this 1.0 times 10 to the negative 5. Now you need to solve it. Now, there are two ways to solve it. One would be, the quick way of doing it would be, assume that x is pretty small compared to 0.20. So that way you don't have to do quadratic solution. Assume x very small. Assume that x is very small compared to 0.20. If that is the case, 0.20 minus x is going to be 0.20. So in other words, I'm going to ignore this x because this is pretty small. So we're going to use it as 0.20 because that would make my calculation a lot easier. 10 to the negative 5 equals to x squared by 0.20. And from here you can solve for x quite easily, and that value, I'm going to copy that value for you, 1.41. So you can double check my calculation, 1.41 times 10 to the negative 3. Negative 3 molar. Now x value is nothing but H plus, and that's what we're interested in. So that's equals to concentration of H plus. So from here I can get pH. pH equals to minus log of this number, 1.41 times 10 to the negative 3, and that would give me 2.85. And that's the answer that I get for this problem of weak acid. So the key thing to learn here is there is no 100% breakdown here. Only part of this will break down, and depending upon how much breaks down, you get same quantity here and here, as long as coefficients are all the same. Then you set up an expression like this, and then finally here we ignored x from the bottom by assuming that x is very small. Now the question is, how small is very small, and when this assumption is right. If this is valid, this is a good assumption if x is less than 5% of the value you subtracted from. 5% in this case, 5% of 0.20. Okay, and in this case, yes, it's less than that. So this is okay. I don't need to do quadratic. Otherwise, you'd have to solve by quadratic method. So many calculators have this quadratic, can handle the quadratic formula, and you'll have to use them. Use that formula in that case when this value x is more than 5% of 0.20. Of course, in every problem like this, you can use quadratic formula, but you don't have to, because they would give you almost the same answer. So far we discussed about pH of a strong acid and pH of a weak acid. So now we're going to discuss about pH of a strong base. That's number 5. Again, this is a pH calculation. pH of a strong base. Now remember, strong base, calcium hydroxide, sodium hydroxide. Let's write down a few of those. Sodium hydroxide, calcium hydroxide, potassium hydroxide. They're all strong bases, having group 1A, 2A hydroxides. They would break down 100%. So let's pick one of these. Calcium and strontium, they belong to the same group, so both are strong bases. Let's pick the strontium hydroxide for this example. Say we are giving you 0.10 molar strontium hydroxide in aqueous solution. So your setup is going to be like this: SrOH2 giving Sr plus 2 OH minus. These are all in aqueous solution. AQ, AQ, AQ. Now, initially it's going to be 0.100. That's given. That's given in the question. And when we added, there was nothing. There was no Sr2 plus or OH minus. It didn't get a chance to break down. At equilibrium, that means you wait long enough so that it broke down and finally remained steady. Question is, would you consider X here? X amount of this broke down? Answer is no, because all of this would break down. So even if you consider X, your X would have the value of 0.100. So the whole thing would break down because it's a strong base. So how much would be left here? 0. Next question is, how much of Sr plus you're going to get? Look at it here. This is the balanced reaction. It's 1 in here, in front of this is 1. This is 1. But this is 2. And products would be formed according to this stoichiometric ratio. So when one of these breaks down, you get 1 of Sr plus and 2 of OH minus. When 0.10 breaks down, you get same number here, 0.100, and you get 2 times that quantity as OH minus. So that would be the first step. If I had 1 in here, I would have 1 times 0.100 would be same as 0.100. Now this time, we're interested in this number in order to get pH calculation. We're going to first calculate pOH, because that would be given by, so pOH, just like pH, minus log of OH concentration, OH minus concentration. That's pOH. So in this particular case, it would be minus log of 0.200 molar. It's 2 times 0.10, that's 0.200 molar. And then finally, you get this number. I'm hoping that my number is right, 0.69, and you can always do independently. And first try to understand what we are discussing here. 0.699. The pH value, you can double check by using your calculator. pH should be given by 14 minus pOH. That's the formula. Let me show you the formula. pH plus pOH equals to 14 at 25 degrees centigrade. Normally we expect temperature to be 25 degrees centigrade. So if I want to calculate pH, it would be 14 minus pOH. So 14 minus 0.699, so it's going to be 13.3. So the answer to this question is 13.3. So first you get pOH here because you got OH minus. There is no equilibrium that I need to set up because all of these broke down. If I had only part of this broke down, then I'll have to set up equilibrium expression, because there is no equilibrium concentration of this left, because it's a strong base. Now we are going to show you a calculation pH of a weak base. This is going to be our 6th calculation. Now again, let me remind you, weak base, strong base, we discussed about it, 100% breakdown. Weak base, only part of this would react with water. So let me show you first what are these different weak bases. And we already talked about the strong bases, all hydroxide. Group 1A and 2A hydroxides are strong bases. Now, nitrogen containing compounds are weak bases. Ammonia is one of them. They usually have, nitrogen usually would have 3 bonds, like this, H, 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 and a pair of electrons. That's an example of a weak base. So let's write down weak base. What are the other weak bases? Mostly they have nitrogens. These are all organic bases. So let me write down one of them, and then we're going to write down in a shorter form. Say you have a CH3 and NH2. Remember I said that nitrogen must have 3 bonds, 1, 2, 3, and a pair of electrons. You don't have to know this name, but this is called methylamine. I can write down in abbreviated form, RNH2. R stands for this, NH2. It could be, I can have even a bigger structure, bigger compound, but still I can write down RNH2. Similarly, I can have something like this, say CH3, and here I would have another CH3, then I have one more hydrogen and a pair of electrons. Dimethylamine. So rather than writing down that or worrying about details, you can just write down R2NH. These are all bases. In the same way, I can extend it to R3N. So these are all, these are symbolic formulas, not actual. R doesn't represent anything, so it could be anything like methyl, ethyl, propyl, any of those can be represented by R. So ammonia are different substituent groups attached to this ammonia. By replacing hydrogen, you get weak bases. So these are all weak bases. They would give similar reaction. So let me show you one typical reaction. R, NH2, and I have a pair of electrons. Reaction with H2O. Now, I can better explain this to you if I write down H2 as HOH. Okay? And I can write down H as H plus, O as OH minus, just to show you where this electron pair would go. In this kind of reaction, electron pair donate to hydrogen, which is being positive, and OH would get separated. So your end product is going to be like this. R, NH2 is no longer NH2. It picked up the hydrogen, so it becomes RNH3. And then since hydrogen is plus, so it gets plus. Okay? So NH3 plus and OH gets separated. So this is the typical basic reaction involving organic compounds. And in your exam, you mostly see weak bases of these kinds. So it would give you a typical reaction like this. Okay, so now let me write down with equilibrium sign. As an example, let's assume that we have a weak base of concentration 0.100. 0.100 molar is given. It's initial value. So initial value 0.100. This is water. This is liquid in excess. Solvent is usually in excess. There was no products at that time. At equilibrium, this is not a strong base. So there will be no 100% reaction or 100% breakdown. Only part of this is going to react. X. So we consider it to be X. So 0.100 minus X is the leftover. That will be the equilibrium. Ideally, when one of these reacts, it's going to grab one of these, one of the water molecules will be involved. So when X is going to react, there will be X amount of water that will be dissipated. How much of this you're going to get? X and X, because of this 1-1-1 relationship. Because you have 1 mole of this, 1 of this. Let's highlight this. one of this and one of this. And that's why when X breaks down, you get X breaks down from here, X is formed here, X is formed here. This is already in excess. It's so much in excess. The tiny bit that goes out of it doesn't make any change. So basically, you can ignore this. It's a pure liquid. So just deal with these, the ones which are changing. This change is almost, you can neglect it. It's like you went to Pacific Ocean and got a cup of water. Would the depth change that much? Answer is no, almost remain the same. Same is the case here. X is a small quantity and this is a huge quantity. So it doesn't make any change and doesn't become part of the equilibrium expression. So now let's write down the equilibrium constant. This time we're not going to write down Ka. This is the base having OH at the end. Having OH at the end means it's a basic reaction. So you're going to write down as Kb. So Kb is the same equilibrium constant, but having a base means you have to write down as Kb. So R NH3 plus times OH minus. Let's have a line here. That's the product, concentration on the top, and RNH2 on the bottom, raised to the power 1. These are all power 1. Its coefficients are all 1. Now I can now write down in terms of X. X times X on the top, and the bottom is 0.100 minus X. So that's X squared by 0.100 minus X. Now, but if this question is given, we'll have to give you Kb value, or a value that can be changed to Kb. So let's assume that Kb is 1 times 10 to the negative 5. So in addition to 0.100, let's assume that Kb is given, which is 1.0 times 10 to the negative 5. So that means I can now show you this algebra. 1.0 times 10 to the negative 5 equals to X squared by 0.100 minus X. Again, we're going to make that assumption that X is much smaller than 0.10, so I can ignore X. That means that assumption will be true if it's less than 0.5, less than 5% of this number. Let's, for the time being, assume that is the case. That would make me do this problem much faster. Then we can check back whether X is indeed that small. From here I can get X value, can do the math, take the square root, and the value that I got is 10 to the negative 3. 10 to the negative 3 molar. Now that's X value. X value is OH minus. That's OH minus concentration. Now, again, from OH minus concentration, you'll have to first get POH. From here I can get POH. We'll get POH is minus log of, just like in last example, minus log of OH minus concentration, and that's minus log of 10 to the minus 3, and that equals to 3. But the question is asking for pH value. So pH would be given by 14 minus POH, that's 14 minus 3, 11. So answer to this question is, I'm sorry, this, yeah, 11 is the answer to this question. So this is an example of pH calculation for a weak base. And these are all similar problems. My next problem would be a qualitative one. That means without doing any calculation, can we say which solution is acidic, which solution is basic, and which solution is neutral, especially when you have a salt. Now in chemistry, salt means we should have an acidic part and a basic part. And I'll give you an example. So let's go over those examples. This is example number 7. So this is a qualitative one. That means we're not going to do any calculation. Of salt solutions. That means we should be able to say whether it's an acidic, basic, or neutral. Acidic, basic, neutral. pH of salt solutions. Now let me write down a few compounds. KCl, NH4Cl, K2CO3, CaCN2. Say all these compounds are given and they're soluble in water. I make a solution in water, and question is, what kind of solution are you going to get if KCl is given to you? This is how you come up with these answers. In most cases it's going to work out. In some cases, especially the formula where you have a hydrogen in between metal and the other part, non-metal part, then it's not going to work out. It may or may not work out. But in these cases, it is going to work out. Potassium comes from a base. So what base is that? Think about what base you can know with potassium. We know KOH, so write down. So that's the base part of potassium. Cl, that part comes from an acid. Since it's a salt, one part has to come from a base, another part has to come from an acid. We know Cl is part of HCl, so we can write down that. Then you analyze what kind of base you wrote down and what kind of acid you got. Base, this is a group 1A hydroxide. Potassium is a member of group 1A. So this is going to be a strong base. HCl, now you think about what kind of acid is this. We gave you the list of acids, the strong acids. So it falls under that. So it's a strong acid. So you got a compound which is coming from a strong base and strong acid. Which property is going to be dominant? Answer is neither, because strong acid is strong base. It will make it neutral. Neither acidic property nor basic property is going to dominate because both are equally strong. Now let's examine the next one. I would split that into two halves. Cl separated from NH4. This part is coming from a base, so I'm going to stick in OH. NH4OH is the base. This is NH4 is plus 1 because Cl is minus 1, and that's why it grabs only one OH. OH is minus 1. This is HCl. Now look at what kind of base is this. Is it like one of those group 1A and 2A hydroxides? Answer is no. So that means this is a weak base. It's not a strong base. Weak base. And HCl, we already talked about this. This is strong acid. Strong acid, weak base. Which one is going to be dominant? Obviously the strong acid. So this is going to be acidic solution. Neutral means pH equal to 7. So in this case, first case you expect pH 7. In second case, you know this is acidic. It should be less than 7. So in second case, you're going to get less than 7. In the same way, you can try the other ones. I can do one more. K, coming from KOH, you can write down. CO3, think about an acid that has CO3. You go through that list, you'd find carbonic acid. H2CO3 is the acid. KOH is a strong base. H2CO3 is not one of the strong acids, so it's a weak acid. So obviously this is going to be basic. So basic solution, and pH will be more than 7 at room temperature or 25 degrees centigrade. In the same way, you can try the other one and see whether you can get the right answer. The right answer for the other one is going to be basic. Next would be a calculation. Okay, we're going to do a pH calculation of a salt. pH of a salt. Again, I think we'll keep the same title. This time we're doing a calculation. In last example, those are just qualitative. Just by knowing acidic part and basic part, you can predict what kind of solution you're going to get. Now you're going to do a calculation with a salt. Say the salt is potassium cyanide. It's known to be a highly toxic compound, potassium cyanide. If you just have some idea about what kind of pH you're going to get from potassium cyanide, this part KOH, this part HCN, strong base, weak acid. So that will give you a basic solution. So let's see whether we get a basic pH or not. In this question, let's assume that we are giving you 0.200 molar KCN. And so we need to know now, with that given information, what would be the value of pH. I'll show you the beginning of this. KCN in water would break down 100%. This is not, keep in mind, this is not an acid or a base. This is a salt. But group 1A, 2A salts always break down 100%. So it would be K plus and Cn minus. So it's going to be 100%. So whatever K plus you'd get, KCN you'd have, 0.200, you'd have a 0 left here, and you'd have 0.200 here, 0.200 here. In this case, we'll have to examine the secondary reaction, second step of reaction. HCN minus is responsible here for overall change in pH. So I have 0.200 molar Cn minus that reacts with H2O. Remember H2O, we can write down as H plus and OH minus. Cn minus goes with the positive, so we get HCN as a product, and OH minus gets separated. So initially, before Cn minus reacts, keep in mind Cn minus came from KCN. We have X in the water as solvent. Nothing here to begin with. Okay, now at equilibrium, this is not like one of those strong bases. So it's a weak base. X is the quantity that reacts. So 100% of that is not going to react. This is excess, so it really doesn't matter. So we are going to ignore it. And you get X here, X here. Now I'm going to set up equilibrium expression having OH minus at the end. We'll write it down as Kb. So Kb will be given by, now let's write down Kb equals to X times X divided by 0.200 minus X. So we're going to really ignore H2O. So let me write down again this HCN times OH minus divided by Cn minus concentration. These are all 1 reaction. So it's going to be X squared, X times X divided by 0.200 minus X. So this is going to be my setup. Now, I need the Kb value before I do this problem. Kb value for this basic reaction. In book, it would either give you Ka value for conjugate acid or Kb value is conjugate base. HCN, and most likely in book you'd see the Ka value. So Ka value, this will be the given information. HCN equals to, I'm just copying that number. Ka for HCN, that value has to be given before we do this problem. Now, if this is 4.9 times 10 to the negative 10, this this is just an example. If my number is wrong, it doesn't matter, but at least we can find out how to do this problem. Here, Ka value of HCN is given, but we need Kb of Cn minus in order to do this problem. Now, there is a formula given in the book which says that Ka times Kb equals to Kw, which is 1 times 10 to the negative 14. Always K times Kb. This is conjugate acid-base pair. Only when you have conjugate acid-base pair, then this would be the case. This would be true. And yes, these are conjugate acid-base. HCN is the acid, Cn is the base. So this refers to HCN, and this refers to Cn minus. So let's find out Kb. 10 to the negative 14 divided by Ka, and we know the Ka value which is given, 10 to the minus 14 divided by 4.9 times 10 to the negative 10. So that gives me a value of 2.0 times 10 to the negative 5. That goes in here. So what we calculate is the Kb, which our given information didn't directly give me Kb, so I had to calculate that from conjugate acid-base pair relationship. And I'm going to plug in that number, this number here. So now we know this is 2.0 times 10 to the negative 5. So what are you going to do next? Assume that x is small compared to 0.200, and then do this problem, solve for x, and I can give you the value that I got. You can double check that x is 2.0 times 10 to the negative 3, and that's going to be OH minus concentration. From here you can calculate POH minus log of this quantity, and then once you get the POH, then you calculate pH by using this formula, 14 minus POH, similar to the other ones. So this is pH calculation of a salt, where you first did got rid of potassium out of Cn minus, because potassium is a spectator ion, it doesn't react. Now you may be wondering that why we are not considering potassium plus reacting with H2O. Let me give you some background so that you know why we ignored K plus reacting with H2O. If you indeed think that K plus reacts with H2O, HOH, then this is a plus, this is minus. K then will go with OH. So then you'd have KOH plus H plus. So let me write down a little bit to the left. K plus H2O, then you'd have KOH, this is H plus OH minus. And look at here, if you can think about a reaction like this, then this would be a strong base, this is H plus separated, already strong acid. A strong base and a strong acid would quickly go backward. So in other words, reaction like this would not happen, and that's why we ignored K plus. That would be the case with sodium hydroxide, calcium hydroxide. Leave out calcium plus, sodium plus. So they are not going to hydrolyze, but this negative part is going to hydrolyze. And then we set up this expression, then we got Kb, then we found out that we don't have Kb value. We have to calculate based on given Ka value of conjugate acid. And then once you got Kb, you did the math and got the pH. So this is the end of this part of this review session. We'll continue this for other parts of this review session.